Hello everyone. In this session, I'd like to explain the atomic structures. First topic is the hydrogen atoms. Second topic is the Zeeman effect. Third topic is the electron spin. Fourth topic is the exclusion principle. And last topic is the main electron atoms. First topic is the hydrogen atoms. So in a Bohr models, is a mixed description with the classical physics to describe the motion of electrons around the nucleus and the new concept of the quantized angular momentums and the localized point particle of electrons we use to build the Bohr models. We have already found the fundamental equations for the quantum mechanics, Schrodinger equations. So we are going to apply the Schrodinger equation to find out the structure of the hydrogen atoms. In the real world, we need to solve the 3D Schrodinger equations. So 3D Schrodinger equations is expressed minus h bar squared over 2m round square c round x squared plus round square c round y squared plus round square c round z squared. This is correspond to kinetic energies plus potential energy C equal energy C. This is a Schrodinger equation in the 3Ds. We are going to consider hydrogen atoms. In the hydrogen atoms, nucleus is located at centers. We could use a spherical coordinate because of spherically symmetric structure of the hydrogen atoms. So we could convert from the Cartesians x, y, z to the spherical coordinate r, theta, phi. Instead of x, y, z, we can use r is a distance from the origin, and the theta is the angle between the z-axis and the radial vectors to the point in the space. If you find the projection of the radial vectors on the xy planes, so angle between the x-axis to the projection of the radial vectors on the xy planes form the angle of the phi. So instead of x, y, z, we could express the Schrodinger equation in the spherical coordinate. Then it becomes this equation. If you take advanced calculus, you have a chance to learn the expressions in the spherical coordinate. And the potential is expressed the Coulomb potential between the nucleus. Nucleus is actually a proton. Proton is located at the centers, and the electrons. So this is a Coulomb potential between the proton and the electron. Then to solve these questions, we applied separation of variables. We use a method of the separation variables to transform the Schrodinger equation into the three separate ordinary differential equations. So first of all, C is expressed the product of the two functions of R. R is a function of only R. And the capital Y is a function of theta and phi. Then we can substitute this equation into the Schrodinger equations. So maybe I can show you. Minus h bar squares over 2n 1 over r squares round r r squares round c round r plus 1 over r square sine square thetas round thetas sine theta round psi round theta plus 1 over r squares sine square thetas round second derivative with respect to the phi plus u psi plus e psi. Then you can substitute psi is a function of the r, capital R is a function r, The y is a function of theta and phi. Substitute into these equations. Then it becomes y 1 over r squares. Instead of round, we use a d because the r is a function of r alone. So r squared dr plus r over r squares sine theta round theta sine theta round y round theta plus r over r square sine square theta round y round phi minus 2m e minus u over h bar squares ry. And then you can multiply the r squares over r capital Ry, the both sides of the equation. And then you will get 1 over r d dr r squares dr minus 2m u minus e r squares over h bar squares plus 1 over y 1 over sine theta round theta sine theta round y round theta plus 1 over sine square theta. Second derivative of y with respect to the phi is going to be 0. And the first term is a function of r alone. And the second term is a function of theta and phi. So to satisfy this equation, actually you can change the r without changing the phi and thetas. Then second terms is going to be the constant values. To satisfy this equation, both terms have to be the constant. So we name it a constant value is L times L plus 1. So to satisfy this equation, this becomes minus L plus 1. So this is a constant quantity. We have two equations. These equations, and also we have this equation. So from the single equation, we derive the two equations. And then look at the green circles. This we call the angular equation. Y is expressed the product of the two functions of the theta and the phi, capital theta and the phi. Then substitute. So sine theta, round theta, sine theta, round y, round theta, plus second derivative equal minus L plus 1 sine square theta y. Then you can substitute. Theta is a function of thetas, and the capital phi is a function of phi into this equation. So then it becomes phi sine thetas d thetas sine thetas d theta plus capital theta second derivatives equal minus L plus 1 sine square theta phi. Then divided by the theta and the phi multiply. So it becomes 1 over theta sine theta d theta sine theta d theta plus L plus 1 sine square theta plus 1 over phi second derivative phi with respect to phi is going to be 0. Again, first terms is a function of theta alone, theta, and the second terms is a function of phi. So each term has to be the constant. So we name it, this is m squared. This is going to be minus m squared. So boundary conditions. So from the angular equation, we have these two equations. We'd like to solve these equations. In this lecture, we are only consider these equations. So by solving this equation, it becomes phi's exponential, im phi's. We can apply the boundary conditions. This is x, y, z. This is theta. This is phi. By circulating, rotating around the z-axis, by changing the 2 pi, it returns to the same point. So phi plus 2 pi should be equal to the phi. By considering these boundary conditions, we have this relation. So if you use the Euler's relation, this becomes cosine 2 pi m plus I sine 2 pi m equals 0. To satisfy these equations, this have to be the m, have to be the integer. So m into the integer. So for the m, it can be 0 or plus minus 1 or plus minus 2. So we have two more differential equations. But these two differential equations might be a little bit too difficult for these lectures. So it's beyond the scope of the present lectures. If you are really interested in the quantum physics, you might have opportunity to take my advanced course. Then we could study how to solve these two differential equations. And I'd like to show you the answers. Finally, we have wave functions and energy levels. R is a polynomial in the R times the exponential minus alpha R. We call it, this is a Laguerre functions. And the theta is a polynomial of the sine theta and cosine theta is expressed as Legendre functions. And the phi is the exponential im phi's and m is the integers. Then energy level is expressed by solving the Schrodinger equations. We have this equation. This is exactly same expression for the energy level with the Bohr's models. So we could confirm that our Schrodinger equation has the same result with the Bohr's model. And we could successfully explain the observational result. Okay, this is the end of this session.